very much that I would like to repeat the same thing when conditions are conducive to do some other time, same type of services. But anyhow, thank you for nice presentations. And then probably since I don't know the audience here, I prepared it in a very simple way. It doesn't mean in any way that you don't know about the sample size and power. This is simply for discussion purposes, just to discuss. So let me know. And then just to give you some directions or something that you haven't probably thought about. So I'm going to go overall about sample size, and then please stop me whenever you feel that you have questions or comments. So that'll be good. Let's see. So sample size and power calculation is really the basic pillars of biostatistics and any statistical works, as you know, because of well-known reasons. So if I now that is because, as you know, we always encounter research questions. So then we try to answer those research questions, whatever the case is. Whenever we apply statistics or biostatistics for any type of work, there are some research questions that we'd like to answer behind. So that's always the case at the background. Without research questions, without problems, why do we study? Why do we even do any type of analysis? So there should be some research questions that we are interested in. So those research questions, and find what the outcome variables are, what the type of interventions, what type of treatment, what type of covariates, what type of outcomes that would help us to answer those research questions. Then as a biostatistician, then our interest is really to measure the effect of, for example, whatever intervention or treatment covariate on the outcome, really to answer the research questions. That's what we do in biostatistics. And then if that is the reason we're doing any analysis, then there are different techniques in statistics that help us to do that. One of those is statistical inference. So statistical inference help us to find if the effect that we see in our study is really true or simply just due to chance, or is it fake or true? And then that's a question that we always encounter. So we try our best to reduce the possibilities of that. Can you hear me? Everybody okay?
Yeah.
Yes.
Okay.
It is okay.
Okay. That sounds good. So, so to find out whether it is really true or simply, yeah, there is some background noise.
Okay.
Is that right? You guys are at home right now. That's what I do. I'm now. Now I've been almost for 8 months now. I've been working from home. I'm teaching online. I'm doing my research and any type of conference online. So I'm used to that. You're doing also the same thing probably. Okay. But anyhow, going back to that, so we need to make sure that we can eliminate that any effect may be due to chance, but we can try to reduce it. So in order to reduce that, then we plan our studies by using randomizations or blinding, as much as possible to reduce that. That the effect that we see is simply by chance. And that is not enough by itself. Okay, whenever I talk about randomization in all sample size, as you guys know, It is about different types of designs. Okay, some of them are probabilistic designs, some non-probabilistic designs, but those things are very important. So using those randomization concept to reduce that. The other element we use to reduce bias is to have an adequate sample. Okay, to find the right sample. Otherwise, we may end up with a fake result. And in a way, so there is one other common sense that the larger our sample size is, the better the results will be. Okay, so that's usually so. The more we have, the more information we have about our population. So the closer we become to the truth. So that's the idea. So then, in order to reach that level, what sample size should we use really to get a value which is close to the true effect? So that's really the questions that why you guys are here also. Okay, how do we decide the sample size big enough that helps us to reduce bias? Okay, so this is the diagram. As you can see on the left here, if you see my cursor here, this is just a representation that we have a population of individuals here, and the size of the population is known, let's say the capital N here. So if we do a census, that's a complete enumeration of all the characteristics of these individuals in our population, we can really get the parameters like mu, variance, correlation, regression coefficients, whatever we have, we could always get those true values. But as you know that conducting a census is just difficult because of it's costly. Sometimes we may not be able even to do it if we have even money. So we end up getting a small sample, the one you see on the right side here. Depending on the size, we determine how many to include here. So we focus on sample because this is manageable. Then from this sample, we calculate statistics. And then from this statistics using probability, we can go back and infer about the larger population. That's the whole concept of probability, statistical inference concept. But now the size of this sample is very important. And then, so that's why we are talking about how we decide that one. And one thing is clear here, the larger the sample, the larger it becomes closer to the larger population, so we'll be better off. So that's a concept. So this concept is based on what is called law of large numbers. This is called the law of large numbers, as you guys know. So the larger the sample size or the number of observations, the more accurate the estimates of our effect. Remember, then we have a research question and we are interested to estimate that effect for that research questions for the whole population. So this law of large number, that's as you remember that the larger the numbers, okay, all means, then we become closer to the true value. That's really the concept behind finding an optimal sample size. Okay, if there is no any question, I'm going to continue. So this is it's not in any way that means that you don't know about this. I'm just going through this. Okay, so why does sample size matter? Because of this law of large numbers. So we have to have a reliable and accurate representation of the population as much as we can. And then also there is an associated with that is we want to have the statistical power or to prevent a type 2 error, false negativity. We'll talk about that later. Finding the right sample size is is really needed at the same time. Okay, any questions? Is there a question? I hear noises.
Okay.
It's okay? Okay, go. Okay. Okay, let's see. So I keep on now. One thing to keep in mind here is representativeness and reliability may not be the same. So whenever we talk about the sample size, the larger the better, right? So the sample size has no direct relationship with representativeness. So that means you could have larger, you believe that you have a large sample drawn from the population of your interest, but that by itself, just the largeness of the sample by itself does not represent a representativeness, does not show representativeness. And that's why you need to design. So it's another one people usually don't talk about. So the experimental design or the survey design is very important. Okay, so to make sure that your sample is as representative as possible, the population that you are trying to study. So I'm not going through that. So there are different types of designs that helps us to make sure that the sample is representative. Okay, beside the probability. So those designs based on probability and non-probability, but there are different types of designs to make sure that it's representative. But the size of the sample measures the reliability. Definitely, the larger we have, the better. So, as I said earlier, that the statistical power is simply a probability that detect an effect if the effect is present. Okay, that's very important. So this is a conditional probability. Statistical power is a conditional probability if the effect is there. So the chance or the probability of detecting that effect is called statistical power. Okay? So these concepts would then is related with sample size also. Okay, because as the sample size increases, the power also increases. Here is something you guys already know. Decisions. Then let me divide these things. On the left side, some definitions that all of you know. We have type 1 error, type 2 error, power, and truth center. So the definitions are given here under that. For example, the type 1 error is the probability of incorrectly rejecting a true hypothesis. So usually denoted in studies by alpha. Alpha is commonly used. This is a false positive. Type 2 error is also a possibility that the probability of incorrectly failing to reject a false null hypothesis. So that's an error that we have to worry about. And then 1 minus the probability of type 2 error, it just happens to be power. That's how it's defined. So the probability of correctly rejecting a false null hypothesis is power. That's a definition. And then when we have the probability of correctly failing to reject a true null hypothesis or true negative term. So on the left, there's a table just to summarize these definitions here. So in hypothesis testing, we have a null hypothesis and an alternative hypothesis. The null hypothesis could be true, could be false. And then based on our study, based on our sample size, then we may be able to reject the null hypothesis or fail to reject the null hypothesis. So that these are decisions that we may make based on the p-values. Now, what happens here in the table? Let's say that conditionally, if H0 is true, if the null hypothesis is true, and then based on our study, based on results, if we happen to reject the null hypothesis, so we make an error here. because if H naught if the null hypothesis is true, we should have accepted it in a sense, okay? But instead, if we rejected it, so that's an error. This is what is type 1 error, which is false positive. If conditional on that H naught is true, but it just happened that we just we failed to reject H naught, not reject H naught. Then that one, the H naught is true. We didn't reject H naught. So that's a correct decision. That's 1 minus alpha. All these are. Now remember, if I sum the probabilities on the columns here, I get 1. So that tells you that's a conditional probability here. On the other hand, if H naught is false and we happen to reject H naught, so that's a correct decision. So that's what we're talking about, power. And if H naught is false and then we fail to reject H naught, it's also make an error. So to type 2 error, which is a false negative. Okay, all these things graphically we can look at. Nothing new. You know already this. So that under we have, let's say, a normal distribution or a symmetrical distribution under H naught, under H1. So we have here either it is H naught or the alternative here. So a lot of possibilities. All these are statistical construction. So these are in probabilistic terms. And nothing is about the reality, but what we're trying to conceptualize really what it should be. So as you can see at the bottom that if the null hypothesis is true and then we rejected those things, so there's alpha at the bottom here, there, the beta, 1 beta. So this is the interconnection. All these graphs, now you can move the sizes of these graphs as you increase sample size or reduce the sample size. That's good to do that. I mean, if I increase my sample size, how this relationship between false positive, false negative, correct results, and all these things, how they shape up. So it's good sometimes to play with that. Okay. Okay. Now that's a background. It's a background. So I'll raise them. I'm gonna use R. I hope that all of you have access to R. Briefly, as I said, that I prepared these slides in a very general form because I didn't know the audience, but for the discussion purposes. No, now we want to sample size. So we have to determine how many people do I need in order to have a good chance of finding the effect. So that's the effect. What is that? So I have to worry about the power. So what is the chance of finding an effect if really that effect is true, is there? So I have some sense. Okay. Another important concept is called effect size. So how big does an effect have to be in order to find it? Now we know that the effect is bigger, so it's visible. So a small sample may be able to do it. If the effect is small, so then really to find it, we need a little large information here. Significance level, type 1 error, which about that is usually specified ahead of time, ahead of the research. So that's important. The type error is related to the power, so they're connected anyhow. So what is the chance of missing a real effect? Another important thing is standard deviation. So what does this mean? How much variability is there in the outcome after I adjusted for the effect? If I take the effect, the impact of the effect out, okay, the impact of that out. So what is the remaining? residuals. So that's the variability is important to do that. So let me put these things together here. Let's see here what I mean here. So the first one is called signal. Those of you have physics background probably know. So that's a signal. That's what we are trying to find out. Signal. The effect of size, scientific of interest. So effect size, how big the effect we want that to be. So that's the signal. But the signal is clouded by noise. Okay, so there is a noise. So some there's some sort of heterogeneity and noise. So this is called variability, heterogeneity, different. Okay, all these things. So we need also to know the magnitude of the noise and also the signal. If you take the ratio of these two, signal over noise, on this side, if you see my cursor, signal divided by noise that's what is called effect size, standardized effect size, or CONT'D. Cons use this. This is a very popular guy, sample size finding, so that this standardized effect size combine the signal and the noise together. So sometimes you may be able to find how much the difference should be, and then also you may be able to find a measure of the noise from past researches or experience for some reason, and then you can then divide the effect that you were trying to detect divided by the standard deviation. That will give you this standardized effect size or signal noise D. Okay, that's something important always. So we can now, it's just understood that in most cases, a power of 80 and above is acceptable, particularly for agencies that would give money. If you show that the sample size is big enough, and then to give you an 80, at least 80 and above, probability of detecting when the effect is there, so they are happy about that. And the significance level, usually 5%, and then you can check percent if you want. And the alternative hypothesis, this is between one-sided and two-sided. Okay, the sample size also is get affected. So you have to specify these things, and that will help you to come up with the sample size. Okay, now all these different parts here are required from you as a researcher, as an investigator. But once you have that, you don't have to memorize the formula or look into this. So all these things are now, these days, are available in softwares. I mean, in programs. There are a lot of programs available now. So we can use those things. Now, one thing to just as a reminder, this CONT'D, a lot of people are using this, even though there are some other modifications. Now they say that if effect size, so this effect size is the ratio of the signal to the noise. If it is small, like 0.2, turning like a small effect, like 0.4, 0.5, like a medium, like 0.8 and large effect size. Sometimes, and then you will see some examples how sample size is affected by changing these sizes. But anyhow, he came up with this simple way of deciding whether you have to have small, medium, or large effect sizes. Okay, in some cases, you could do that. Okay, I'm gonna stop here. So we talk about the software now. So it's pretty much help us to calculate the sample size as long as we are able to provide those different elements. Okay. Okay. If there's no questions, probably after I finish that we can discuss. But anyhow, please stop me if you have. So there are some softwares that for some of the standard problems. I I put them together here for today's discussion here. If you are able to see, but it's a lot of things. But one thing for sure, our program is freely available. So wherever you are, as long as you have a computer, you can download. It's a very powerful program. It does a lot of things, so it's really available. The other ones are expensive and all these things, so it's free. So we can always use that as a first. So there's a power package that right now, if you guys have computer, you can download, and then we can work together if you have time. This power package, you can Google this power and then open R and install this power. This one is based on the cohorts, those small, large, standardized effect sizes. So they are based on that, and then as you can see in the right column here, it has the most commonly used comparisons, tests for for example, if you have two proportions, like for two population proportions, equal sample size, unequal sample size. If you want to have ANOVA and a chi-square test, general linear models, not generalized, but general linear models, one single population, two populations, more than two ANOVA, and then correlations, and then if you have sample mean, paired, independent sample, independent to sample test, and paired, something like that, or with unequal sample or sample. All these are possibilities that you could have and practice. If you have already used this one, that's fine. If you haven't, then I encourage you just to look at them, okay, and then see. You may encounter needing these things. So these are very standard, simple approach for simple comparisons, and the sample size and or power associated with that. And then, but I'll talk later about the complex ones. So most of the time, you may encounter things that these may not be enough to calculate the sample size. That's really what I would like to talk about. I'm not going into the details, but I would like to talk about, okay? But for standard formulas, for a standard simple two population, whether it is binary outcome or continuous outcome, you can do that here using these nice formulas. So let me show you how this one works. So if you take one of those, for example, here's power t-test. This is a program, and power that's in R, you get that. So let me go, this is a formula. If you just Google these things, you see exactly what I just put it here. Here you see the sample size. Null means, you have to fill it. You can ask. So you can provide. So for these functions, either you provide the sample size, and these standards for standardized effect size and the significance level. You can change this also, but that's mostly standard. And the power is also null here. And the type of test, is it a two sample test, a one sample test, or a paired sample test? Okay, so you can pick any one of these. What about alternative? Do you have a two-sided? You know what I'm talking about. So this is, or is it left-sided? Greater means right-sided. So you can pick those things depending on that. Okay. Now here, as you can see, there is a null. That means, now, for example, if I just leave n, if I don't provide the values of n here, but I provide the effect size, for example, the medium, which is 0.5, let's say, and the power is 0.8. So that 0.8 is 80 and above is okay, it's acceptable. And it's a two sample. If I pick that and a two-sided, and then since I haven't provided for n, it will calculate the sample size that corresponds to that size, to that power, and the alternative. But if I supply, for example, the sample and the effect size, and they leave the power here empty or null, it will calculate for me the corresponding power for a particular sample size and effect size. Okay, so it's flexible these days. Thanks to some programmers, I mean, they make it available for us to use. So here is an example. This, you may not be able to see it. I forgot to expand it here. I hope you can see.
It is visible, Prof.
It's
okay. It's okay. It is visible.
Say it again.
It is
visible. Okay, good. Thank you. Yes. It helps to be young. You guys are younger than I can see. Okay. So that's good to me. That's good. Okay. But anyhow, so so you have to download the power PWR in R, install that, and then in order to use it, you say library, bring that. Okay. You generate the functions, and then I'm just gonna go to one example here: power t-test. Then here, the effect size I picked 0.5, medium. Power is significance level is 0.05. The type of the type of comparison is example one sample, two sample. The alternative is two-sided. Then just run this. If I run, I get the results here. So here it gives me a two sample t-test power calculation. And then the sample size gives you here 63.7. The D is already level is provided, power is given. The only thing, as you can see there up, I didn't specify N. Whatever missing, it will calculate for you power. So they calculated the sample size for that because I provided already the power effect size. So this is N is the number in each group. So you need 64, at least 60 individuals in one group as another group. For example, in control and in the treatment group. In order to be able to detect an effect size of 0.5, standardized effect size of 0.5 with a power of 80%. Okay, something like that, two-sided. So you can play with these things with all the other ones also, if you encounter, or if you want teaching class for students, so they'll then practice with these. Okay, the different types of things you can. Okay. One other thing is we can, I'm going to show you also, but here I just put 0.5, right? Then what happens if I change those, what do I get? Sometimes it's a good thing. I'll talk about that here. So supposing now we look at the effect size, okay? I want to see at the different values for effect size and see the corresponding sample size. So let me create that. For instance, create a table with effect size ranging from 0.2 to 1.2 and compute the corresponding sample sizes. And sometimes this is helpful also. So if you do that, here is how you do it. Here I have Dagne has two values. I create an object here. So for I, 0.2, 0.3 up to 1.2, all these different ranges here. I calculate the power for each one of these with the same, effect size changes. See that the effect sizes from 0.2, 0.3, 0.4. So the D value equals I. So wherever the first round, 0.2, and so on, goes through that, I fixed the power at 0.8, the same to sample alternative. And put these things together and see if you just highlight the whole thing and run it or cut and paste in your program in your R, you can see what I'm talking about. Here is the results that you get. What you hear is the first column here, the one in my arrow here. Those are the effects sizes. 0.2 goes to 0.3 up to 1.2. And the one on the right side, the column, then you see that those are the corresponding sample sizes. So I can see that as the effect size gets smaller and smaller, so then a larger sample to detect that effect. The effect size is big, visible, for example, then you need a small sample size to see the effect. So that's, you can see that you can plot these ones and look at also. Why this is important in some cases? Because you don't know which effect size really you may want to use. Okay, when you write a grant, or when you're trying to send, in that case, you can show the reviewers that now if my effect size is, let's say, 0.6, I need at least 45 individuals. If my effect size is 0.3, I need 176. You see that 0.3. So if I want to detect a very small effect, I need this many individuals. Okay, so then one other thing here is, as a biostatisticians, we don't know a lot about what is really what type of, or what value of the effect size is really meaningful. But experts in the field, they know. For example, if you ask experts in a different field, they can tell you that if you are able to show this much difference between the one in the treated group and the one in the control group, then they will be happy. But if you see this much effect, they don't believe it. I don't think that the effect is that much small or that much big. Okay, so they have some idea what the level of those would be. So based on with their consultations, then you can pick the corresponding sample size. Okay, sometimes it's good to do that. Okay, this is using the simple standard available formulas which are already programmed. The softwares are available, so we don't have to compute them, can get and look at them. But now you may ask question that the world is not as simple as this, right? Why not? Sometimes we encounter a very complex experiment, complex designs, complex models. Not always a two sample, one sample proportions or sample means like that, or ANOVA for that matter. And then you may have also, let's say, core data, longitudinal data, where you have correlations, and all these ones assume independence. Okay, that's why these are basic, simple approach. So this is my intention to bring these things here. These are already programmed, so we can use them those easily. That's what I'm trying. Okay, now for discussion. So whether now these days, since the computers are powerful, and then particularly young people these days, they are very good at computers, how to write programs, how to understand. So why not we do simulations? So Monte Carlo simulation is so that's is important to look into. So as I said, for simple situations where formulas exist, no real advantage to simulate because those things are However, for not so simple situations, simulation comes into. Simulation is important. So, like, for example, more complicated models can easily include covariates. For example, you're trying to what happens if I have some confounders? What happens if I have some moderators, interactions? I would like to see I can detect the effects there. So in that case, you may have very complex things, not the simple just differences. So you could also have like different outcomes, binary, ordinal counts, all the different types. And then also, as I said, correlated data. For example, if you have longitudinal or cluster data, these are correlated because you have observations from the same individuals over time. So those observations are correlated. So they depend to each other. They depend on the individual. They cannot treat them as independent. In other words, what I'm saying is, and for example, in your study, if for let's say for one particular individual, you have measurements taken at a baseline after 3 months from the same individual, let's say, second visit, third visit after 6 months from the same individual. So you have 3 observations from the same individual. And then these 3 observations cannot be considered as if they are independent because they share the same individual. Now, if you assume those 3 observations are independent, what you are saying is those 3 are coming from 3 different people, from different individuals, which is not the case. So that complex situations happen like that. So that's where, so I encourage you to work on the CARLO simulations if you haven't done before, to be familiar with how to do this complex on the power and sample side. Still, R has a program. I'm going to leave that with you. So here, WR, we talked about that. Those are for simple statistical models. But for complex models, parameter test package and Geoffrey's is good. So you can download these, and there are manuals, tutorials on how to do those things. You can go through that, and for different types of modeling. And then, so the idea here is just to go over that. Whatever those parameters, so models, you can do the repeatedly generating random observations based on predefined designs. For example, if you have a logistic regression and then your outcome is binary, you have a bunch of covariates, okay, some risk factors, confounders, okay. You want to include those things, and then you, on top of that, you have treatment effect. You want to compare one group against another group after adjusting for all other confounders or other risk factors, whatever, okay, or demographic variables. So that's what your regression model looks like. But now you'd like to find out what is the minimum sample size that's needed in order to reach the difference between one group and another group this much. Okay, a standard effect size. So what do you do with that model? You generate random observations from that predefined model. Okay, you start with a model with all the values there. So then whatever effect size you are looking for, generate samples from that. And then once you generate that sample from based on that generation, so you analyze each data set generated according to your model, count the proportion of results that are significant. Okay, for that effect size, you like if the p-value happens to be less than 0.05, you count those. for the repeated. You can do these things 1,000 times, 5,000 times. You know, the computers these days are faster. You can do these simulations over and over. And the proportion is the estimated power for the model. That means if it exceeds 80%, then take the corresponding sample size that gave you at least 80% power. So that's the sample size that you need to have in order to have in order to detect the effect size based on your logistic model, for example. Okay, these are something that it requires some sort of lab to do these things. You can do that, but I encourage you to practice with this one here. That I'm not doing it right now, but you can do this. And then there are others also. Now I'm almost done. So I open for discussion here. So we talked about the R program, but there are other programs also available you can use. Particularly at the bottom one here, I encourage you here the optimal design. When you have this multi-level longitudinal research for Windows, it's very, really useful. And then I know that Amara, you have been involved in other cases. You may have this longitudinal research trial, something like that. So this optimal design, manual, you can follow that. You can easily follow those type of things and then find the appropriate sample size and power. Okay. So I think I'm done with my brief presentation here, and then it's open for discussions, questions, whatever you have.
Okay. Thank you, Prof, for your brief and precise presentation.
Okay.
Thank you for
Welcome.
University College of Medicine and Health Science. Okay. Participants or audiences, if you have any question, please welcome this time to discussion.
I hope it was clear, right? Okay. Okay. Okay, go ahead.
If you have any question, raise your hand, and I will give you the chance.
Okay, but yeah, ማንኛውም አይነት ጥያቄ አስተያየት say anything.
Okay, Fantau raise the hand. Okay, Fantau, you can ask or raise your concern.
Okay. Thank you, Professor, for your nice and interesting presentation.
Hello, I couldn't hear it. Sorry, Amara may help me do that. Okay, go ahead.
Okay, okay. Okay, okay. Oh, sorry. Mute ሆነ ስለነበር ኦኬ ፈንታው
Yeah, any
ሄሎ ፈንታው
ጥያቄ እዛ ኦኬ
ኮኔክሽን ፈንታው ኦኬ ፈንታው እየሰማ አይደለም ኤኒባዲ አዘርዛ ፈንታውን እየተሰማን ስላልሆነ
ኦኬ
እንደገና እንትንላለን
that's okay
anyone who have any concern regarding to this topic welcome okay man no ሲሳይ ነው yes
wait.
Okay, you can raise your idea.
Okay. First of all, I would like to say thank you, Prof.
You're welcome.
Okay, and your presentation was very interesting, and I think you are also the first to join this seminar from seniors. So I would like to thank again for your collaboration. Saying this, let me ask some question. So in your slide, you said that no sample size doesn't have a direct relationship with representativeness.
Yes.
So what mechanism do we have whether our sample size is sufficient enough in order to represent the population in which we draw our sample size? And this is one question what I wanted to know.
Okay. Okay.
And the
Good.
second is what is the minimum sample size for a research? Probably we may conduct randomized control trial, or we may conduct cohort kind of study or other kind of designs.
Yeah.
So what minimum sample size will be supposed to be sufficient in order to conduct research?
Okay.
And in terms of effect size, I think the lowest is 0.2, the medium is 0.4, and the larger is 0.8. So as the effect size is lower, and we expect the larger sample size.
Yes.
And which is suggested for considering for sample size calculation. Thank you, Prof. Again.
Okay. Okay. Good. Yeah. Okay. That's good. Thank you. So for one thing, that when I was saying that just having a large sample by itself may not be a way of assuring us that we have a representative sample. Okay. So that means you could have a large sample, which is really garbage, for example, in some cases, if you are not carefully collecting information, that could happen. For example, you have a particular target population. For that target population, then the way the population is composed, and then basically dispersed and different, certain type of group of individuals live in a certain region, another region, another region. Just assume that even within a cities like that. And then if you just, because the sample size says, oh, let me just get 100 individuals, and if you just go and talk to people that your friends at the club or church or mosque or at a school, because those things are easy for you to interview them or to get those things. But remember that still your sample size, you can get the sample size large. But that really assure you that your results are representative of the populations. See what I'm talking about? For example, you take Desse, and Desse may have different types of regions. I don't know. I've never been in Desse, so I don't know, but you guys know that. So then in that case, there may be some areas where most people live. So maybe some other areas are well-to-do, a little bit better economically, they may live. Or there may be some places where a certain group of individuals are, they live together in that area, and some others, they may live there, but they are few, something like that. So you may not expect the population, the people who live in this uniformly homogeneous. So wherever you go, you get everywhere. I do that. I probably in this that may be the case, but in some other cases it's difficult. So in that case, if you just happen to get information from convenient for you, okay, for the researcher from a particular area only, then in that case, you can satisfy the requirement for the sample size just because you have large sample. But it's no more, it's not a representative because you don't have every section of the region is not covered as much as possible. So it cannot be representative in that case. So how do biostatisticians guarantee that a sample size is a representative? So that's where you have, this is called experimental design. It's a whole area, experimental design by chance. It's a course by itself in some university. So you might have heard that simple randomized design, you have multi-stage sampling, all these are probability sampling, you have to do those. It's called stratified random sampling, clustered random sampling, multi-stage, all these things, these different designs are used to make sure that every part of the population that you are interested in could have some representations in your sample. See, that's very important to have that. That's what I'm referring to when saying sample size itself is not enough. So you have to have a design also to make sure. The minimum sample size, there isn't any minimum sample size. There is one thing that I just want to comment here. You know, in these elementary school and elementary textbooks and statistics, we are stuck in a long time ago. Okay, we stuck to the 30. If the sample size is greater than 30 or less than 30. If it is sample size is less than 30, it's considered like a small sample. If the sample is greater than 30, it's called a large sample. Those things imagined long time ago. Those are done. When we didn't have much computer at that time and all these things. No, that's not the case actually. So it all depends on the outcome that you are measuring. Sometimes the outcome may have large variance, which in that case you want to have more sample size, larger sample size. In some cases, the outcome could be, so the outcome may have a small sample. Okay, so let me give you an example. If you take 100 individuals, okay, in let's say 100 individuals, and measure their heights, okay, if you measure their heights of these 100 individuals and find their mean, the standard deviation, variances like that, and also from these individuals take their income, how much money they have, okay, from these 100 individuals, and you can find the mean income, the standard deviation of the income of these individuals. Which variable do you think is more variable? Is it the height has more variability or the income? So the income will have more variability because some individuals have a large number of higher income, others may have less income. Height is determined by biology. You could be rich, but you cannot increase your height, right? So it's dictated by some other factors, height. But income is not. If you are close to some individuals and you get more money, you know, it's all different types of things. I don't want to go into that, but I think you can follow me there. So what I'm saying here is, whatever the outcome variable that you are interested in, so it has its own variability. So based on the variability, that's how the sample size. Remember that size is signal divided by noise. So the noise is the variability, very important. Okay. So I hope that answers your questions about symbol. So effect size. The effect size, you can play with that. For example, as I said, there's a signal. If you have very small effect size, in order to see that, you need a lot of information to find out that. Now, Imagine, let me see that is supposing you have, you are looking for something that is hidden there. If it is a small area, then it's easy to find that, you know, what are you looking for. But if it is a larger area, it's just difficult. So the same thing with variability. If there are more variability, there are more noise. The signal, you know, the main thing is hidden by a lot of noises. Then in that case, the effect size becomes smaller. So you need a lot of information to detect it. But if the sample size, if the effect size is big, so you need a small sample to detect it. So that's the, if you look in the slide that showed you earlier, let me see here if I'm able to bring it here. So as you can see that here, for example, when the effect size is very small, like 0.2, you need 394 around that. You see that? Because you need a lot of information to detect. This is small, a lot of variability here. But on the other hand, at the bottom down here, if the effect size is, the standard effect size is very large, so you need only few sample size, like 12 to detect it. So it's all this depends on the effect size. Effect size, remember the effect size we are talking about is how much the differences between the groups, if the signals divided by the variability. Okay, I hope that answers your question.